no way you can ever do a clinical trial without a power analysis. I'm assuming for every dissertation at Alliant, you need to do a power analysis.
I just did one for this time.
There you go. Excellent. Excellent. So power analysis, how many people do I need? I have a couple of contracts with large military researchers, and they have me as what's called a pre-award contract. So one of the first things I do when I work with a client is doing this, doing a type of power analysis. I'm not going to go through my entire 60 slides here because it gets into more detail, but for Alliant, I really did present how you can do power analysis for many, many types of studies. So what's the information you need? Well, got to have an idea of the effect size, the magnitude, variance explained, a mean difference. I got to have an idea of your alpha, which is usually going to be 0.05. What if they have no idea about the effect size? Well, sometimes I'll do it between what's traditionally small and medium, but usually you have to put in a lot of data, everybody, and it really depends upon your design. Usually we use a power of 0.8. You don't have to. But you're going to find that's real generic, everybody. Jocelyn, do you remember what was your desired power you did for yours?
0.8.
Yeah, which means 80 times 100, you'll be sensitive to group differences, or R-squares, which means what's your type 2 error rate? If your power is 0.8, guess what's your type 2 error rate? Yes. Right? So I had one client who was not agreeable to that. He said, nope, I want my power to be 0.9, because he wanted to delimit his type 2 error rate to 10%. So didn't that mean he had to get more people or less people, given he went from 0.8 to 0.9? More, yeah. You had to use more. You got it. So you got to think about that, everybody, in terms of your desired power. Remember, there is a difference on directionality. As we discussed, we showed that example with Zach's correlation, right? So here we have 0.089 for two-tailed, 0.044 for one-tailed. So again, you got to be mindful about directionality. So what are the parameters? Here it gets tricky. Some software may estimate n via a global effect size. Some software, you can put in what you think is Cohen's delta, which is the standardized effect size for two groups. Some you put in an R, an F, an R squared. Some require that you have to put in means, standard deviations, correlations, especially with multivariate designs. And I'm going to show you power analysis. When we get to the chapters on MANOVAs, I actually have in the notes how to do power analysis via SPSS syntax. So where do you get information about your anticipated effect size? Well, maybe meta-analysis. Like here's an example. Relationship of self-evaluation traits, self-esteem, self-efficacy, locus of control, job sat, and job performance. So if you're lucky, you got a meta-analysis that will give you an idea of the effect size. What about if there's no meta-analysis? Find prior studies that are similar. What if you're interested in texting and life satisfaction? Texting's kind of new, relatively. There is some research, but more with distracted driving and so forth. But what about you look at texting and life satisfaction, but there's nothing there yet? What's kind of similar research you might be able to use?
Email?
What? Maybe email. Yeah, maybe e-messaging, email, internet. It's close enough. So it's a start. Or you can do a pilot study. And if you don't have similar studies to access, you may want to be conservative. This is what I do with my clients. If they have no idea, they really don't know, then I kind of do like little simulations. And I do power analysis from small to medium. I do small to medium. I vary the effect size and say, this is what we got. What do you feel comfortable with? What will your budget provide? And so forth. Again, make sure your effect size corresponds to the design. A bivariate correlation for multiple regression, odds ratio, a multivariate effect size. Those are all very different. Don't just say the anticipated effect size is 0.3. That tells me absolutely nothing. And I've seen people do that. They use this one paper by Cohen. It's a Cohen primer, like 1992, and it's not the right effect size. So be very mindful. There's all types of effect sizes. There's all types, everybody. There's standardized. Remember good old Cohen's D, everybody? Group 1 from group 2 divided by the what? Do you recall what's in the denominator? Group 1 minus group 2. What makes it standardized? Standard deviation. And it gets tricky. There's what's called Glaser's D, because sometimes you use the standard deviation of the control group. Sometimes you pool them together. There's non-parametric. Probability of superiority. What if it's a Likert item? 1 to 4 point, where you rate your health. Poor, fair, good health. It's weird to do a mean for that type of item. But there are ordinal methods that can look at 2 greater than 1, 3 greater than 2, 4 greater than 3. And that's called probability of superiority. Or dominance measure. That's a whole other different type of area. Grissom and Kim's book is fantastic. This book on effect sizes, the 2nd edition, is just absolutely fantastic. Correlations. Correlation, the point by zero. Remember what a point by zero correlation was? This will be on your test, Stacy and Ross, coming up in 6022.
I forgot.
Okay, what do you think it is? Point by zero. You remember that from 6022, Jocelyn? Okay, I'll give you a hint. Is it A, Dracula, B, a dichotomous variable, and continuous? Yeah, dichotomous and continuous, right? Male and female with a continuous outcome. That's the point by zero. There's all types of variance explained. R square, omega square, epsilon. Ross and Stacy are getting into data right now with things like partial eta squared, semi-partials. All these variance explained. For this semester, there's multivariate effect sizes. You're going to learn that. And a lot of them come down to a type of partial eta squared, these multivariate effect sizes. Categorical. There's contingency coefficients, number needed to treat. All types of things with categorical. And even odds ratios, which some say is not effect size. And we're going to talk quite a bit about it on the chapter on logistic regression. When we say small, medium, and large, you guys, a lot of it's based on Cohen's 1988 book. But again, remember what I've said, as Cohen has said for years, they're just loose guidelines that help you out. So a correlation of 0.1, 0.3, 0.5 might be small, medium, and large, right? And we've used that in my classes. I use it undergrad. But remember, is that context dependent? Using your word, Jocelyn.
Yeah.
Absolutely, because 0.1, 0.35 might be way too small for chemistry. Let's say chemistry just has much higher effect sizes because of what they're able to manipulate and control. That may be way, 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 way too liberal, right, for chemistry. So remember, these are just rules of thumb. What's a medium in nursing research may be small or large in chemistry, biology, or sociology. So again, what that means is having an idea of the effect sizes given the field. Given the field. So you can do a software, and you can get an idea of how many people you need. How many you need per group. So if you can do small, medium, large, and boy, the sample sizes can be radically different, everybody. Look at this, everybody. If you have a large effect size for 2 groups, if you have a large effect size, wow, you only need 26 per group. Piece of cake, 52 people. Medium effect size, 64 per group. Small, how about that? 786 people. It's really different, isn't it? It's radically different. So you've got to have an idea. Because if you have a large effect, you've sure wasted time and money getting those. If you have a small effect, you've sure wasted time and money and resources. Either way, you've wasted time and money and resources. Which is why this book, let me see if I put it here. There's a chapter on Handbook of Ethics and Quantitative Methodology. Great book, everybody, that you should put on your to-do list. And what does ethics have to do with power analysis? What does ethics have to do with power analysis? I mean, it's a very technical process.
Well, somehow you can manipulate the data. Or you can manipulate not the outcome per se, but maybe what you record.
Okay, I see exactly what you're saying, and your comment has to do more with, there's actually a chapter in this book about reporting and ethics. or even significance testing in ethics. So you're kind of merging both of those bridges, Jocelyn. Right now we're at the sample size estimation stage. Just estimate how many people you need. So you're absolutely right, and that's more forthcoming in the research process. What's the implications of underpowering or overpowering? Why would there be an ethical concern if you under versus overpower?
Because we're discussing getting more people just to make sure we hit our target, even though we have an estimate.
So the problem is, absolutely, so in medical studies, think if you've needlessly exposed people to a medicine that has really bad side effects. Maybe early on, you got your 200 and you've exposed them. Or what if you underpowered and you had a drug or let's say cognitive restructuring intervention for psychologists that could really be beneficial, but you only got 20 per group and they'll never see the light of the day of this wonderful intervention. So there's actually ethical ramifications associated with even something as basic as power analysis. If you under or overpower, you may be subjecting people to something they shouldn't, or you did not get something out to market because of underpower. So do you see where there's even an ethical element for each of these? That's why there's a wonderful chapter here called Ethics and Sample Size Planning. Most people, the examples they think are usually medical studies, but this can pertain to organizations, in business, in any area.
How though?
With organizations, think about subjecting a lot of people to some type of brand new total quality management. You got the TQM version for the new millennium. And they've been exposed to training, they modify work practices, you found significance, you had a large enough sample size, you overpowered, and it had a small effect and it really didn't matter.
Yeah, then you spent a lot of money.
Or an intervention and really could be helpful for delimiting job stress, right? We have one of these hydro massage things, you're gonna put them in the back office, and you didn't need 20 people per group to show the effects, and that maybe could have really helped delimit job stress and hence impact the bottom line as an ROI. It can go, so I can give examples for any field where under or overpowering may actually have ethical ramifications in both of those. So everybody, you're going to find, and as my presentation, there's some cool ways to do power analysis, even in SPSS. A journal called Behavior Research Methods. Here's power analysis for multivariate and repeated measures design, a flexible approach using MANOVA procedure. And I have examples of this in the PowerPoint I've appended. Plus, you're going to see I've put examples in some of the lectures. So, there's also a very important correction paper. If you're interested in these papers by Osborne, 2006. Make sure to get the 2006 paper. So let's say we have a 2 by 3. 2 groups by 3 repeated measures. Here we have 2 groups by 3, and it is a type of multivariate design. So it's really pretty cool using the syntax via MANOVA. This is all syntax, everybody.
What program are you using?
SPSS.
Okay.
So let me show you right here. See if I've put some of this. Multivariate, maybe notes. Okay, let me see what I have here. I don't have it on the notes. Maybe handouts? No? Okay, then let me do this. I'll show you how I can do this. You can just cut and paste. That's right. You can just cut and paste here into the syntax file. So just in the meantime, if you take the syntax I have, and it's also in here. You also notice in my notes, everybody, I've shown how to use SPSS. I have an example of multiple regression, and I show how to do this right here, and there's syntax right here. Syntax right here. There we go, okay? There we go. So this means I have group 3 patient satisfactions, and look at all this information you got to put in. You got to put in the means for the groups for each time.
There's no point and click for this?
No, this is
all.
I
didn't think we could even use SPSS for power analysis.
I know, look at these are absolutely.
You said we had to use some other program.
No, you can use whatever. Oh, GPOWER is great.
Yeah.
Yeah, and I show in my presentation, GPOWER gives you the same results. But it's kind of nice here because you can put in all the same information, but in my presentation you get the same. But let's say you just had SPSS. Do you see? I put in the means for each group, for each time, and I put in MANOVA. MANOVA is the old syntax. If you took multivariate from me well over 10 years ago, you would have kind of had to have done a MANOVA by syntax. Well, 15 years ago, this is the MANOVA syntax. There's no point and click for this. This is what you used to do for all types of studies. But look, if I do this, everybody, if I just get this whole syntax, and I just run it, there you go. Okay, this is add. If I run that whole syntax, for the main effect only, for group, look, it'll give you a power 0.85. But we're interested in the interaction. Add, look right here, everybody. Here's your interaction for group by patient satisfaction. 0.9. There you go, there's your power analysis. So it's pretty cool, you can do that in SPSS, plus you can do this with GPOWER, which I will show you. So it's kind of nice saying, guess what? We're potentially what? If you wanted power 0.8, can I get away with maybe a smaller sample size? Absolutely. Absolutely. So, that being said, everybody, it's pretty cool to be able to do for multivariate designs, these type of power analysis. But again, what does it assume? That you've got a lot of information. You got to put in the means for each time. Now here's GPOWER, everybody. GPOWER, which is free, you can download from the web. You just put in the means for each group, for each time. And what you also have to put in, everybody, and it's in a separate thing, you have to do this thing called the standard deviation and correlation matrix, which means you've got to put in the standard deviation on the diagonals and figure out what the correlation of the repeated measures are. You have to have an idea. I usually use 0.5, 0.6-ish, 0.7. Yeah, I use around there. Because I think, you know, if I measure depression, week 1, week 2, week 3, are they probably going to be related? Probably. So do you see all the information you have to put in for power analysis? Now, true, you can put in just one effect size, but this means you really know your data, and to you, what will be a clinically meaningful result. And when I do this, everybody, I know it's hard to see, but it gave me 90 people, 45 per group, and gave me exactly the same power. 90 people gave me the power. Effect size is 0.38, which is an effect, a type of effect size. And guess what? It gives me a power of 0.9, exactly the same as MANOVA, exactly the same. And I've done a lot of testing of GPOWER, everybody, just to see if it's the same as all these softwares that I've paid for. And it's given me, as you'll see in the presentation, given me the same results. And you'll see I do many, many examples of like one software I use is called PASS, which a lot of the regulatory agencies use. And it gives me the same results. Same results. And SPSS. Give me and the mixed ANOVA, same results. And there you go. Exactly the same as that in GPOWER. So it's pretty cool, everybody. It's pretty cool, and these are all in the notes as well as the handout. So, and here you see from GPOWER, 90 people give me a power of 0.9, which means if Chad says, wow, if I have a power of 0.9, I can get away with maybe 30 people per group. So Chad can just rerun it with 30 per group and see what his power is. So, tricky part. What is a large, medium, small effect size for your study?
That's a tricky part.
Yeah, for your study. Yes, there's many guidelines, but they may or may not pertain. So a great article by Prentice and Miller, when small effect sizes are impressive, and a chapter by Cortina and Landis, when small effect sizes tell a big story and large effect sizes don't. Sometimes something can be so obvious. You so obviously assume there'll be a large effect that somebody will shrug their shoulders and say, okay, how does that extend science? Right? If it's so obvious. Also, science is a small effect when you didn't expect anything. May still, once you put it in common sense terms, wow, that's a 2% reduction in recidivism in crime, which saves $30,000 per taxpayer per month. You know, I'm making things up. You get an idea. Once you start translating some of these into very practical effects, even a small effect size may be practically substantive. What if you found you had a 0.2 standard deviation difference between groups, small effect size, but it resulted in $35 savings per employee? Right? And I found this from a journal article. And this is actually something I wrote for a journal article. Even though effect sizes for some findings were small, there's a body of literature that illustrates how small effects may yield some import. We actually published an article in medical education looking at actually potential bias for the verbal part of the MCAT. We did this with ECSD, and it was a small effect, but the reviewer said, then why should we care if it's a small effect and you have significance? Any of the elements may constitute a meaningful effect size, albeit small. The outcome was anticipated to only be distally. You know what I mean by distal versus proximal? Proximal is close, distal is far away to the explanatory variable, and yet some variance was explained. They call that phenomenon with obscured consequences. Or when some effect is captured even in the subtlest designs, inauspicious designs. And or when the effect size translated some critical metric, decreased mortality, cost savings. So even small effects, you may be able to argue they've got something there. And this is from the wonderful book. See, you have so many great books you'll read over summer. Statistical and Methodological Myths and Urban Legends. It's these ongoing articles that are fantastic, published in Organizational Research Methods, and they actually created a book about these statistical and methodological myths and urban legends. Great, 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 great article. So that's power analysis. I know I went on long about power analysis. I have that whole PowerPoint presentation that may help you with multivariate designs, but it's so important to be mindful about this. And as Jocelyn's had to go through the experience of actually doing it, and all of you will for your dissertation. Now, what I've also done, everybody, is created a presentation on missing data. So you are the first class getting these presentations, which means I left kind of the date when I did this up in San Jose. I'm not going to get into all the technicals, but just like doing with outliers, I know it's hard to see, this is a scanned picture, but there's many strategies you can use for missing data. You have this person trying to get a line, he sees these little outliers, and he just erases them. That's one way, right? Get rid of outliers. With missing data, if people have missing data, what could you do? What would be analogous to this with if people have missing data? Throw them out. Right? Throw out those 20 people with missing data. So you have a survey with 120 people, 20 have missing data. Throw out the 20. You've got 100 people. No, right. There's a lot of problems with that. Now, is there a chance that if any of you do observational or survey research, you may have missing data? What about even experiments? I'm sure you can say, wow, experiment, you should always be able to control and never have missing data. Could you maybe even have missing data for experiments? Why? Why would you have missing data for experiments? I mean, don't you have a guy in the lab coat standing over you, making sure you fill out the survey, and we get all the measures, and I get your blood pressure, and I get your EMG, and I get your self-reported pain scale? Should there not be any missing data, even in a beautifully done randomized controlled trial?
Well, there could be error.
There could be error.
People may opt out.
People can opt out. Can I choose not? I really don't want you to take my blood pressure. Can I choose to say, you know what? I just don't feel up to you taking my blood pressure right now. I don't feel like taking this job satisfaction scale right now. Or they fill out a survey, and guess what they might do, even if they fill it out. And this is going to happen to you guys. Absolutely. They're going to leave some items out. Either because they're
halfway through.
Oh, absolutely. We've gotten that halfway through and they say forget it. Or sometimes it's almost not anything that obscure. Sometimes they miss sections because when it says go to the next part, they don't understand the instructions. Especially what gets problematic is in marketing research, they have a thing called skip patterns. If you answer yes, go to number 3. Have you guys ever seen that? If no, go to number 2. We had a problem with that with the heart failure study, and lots of people were getting confused and realized these people were average age 74 years old, sick people, and they were missing a lot of data, and just taking surveys was hard on them. What we ended up doing, you guys, we ended up shifting it from portrait to landscape. And then, if we had if number 1, we did a big dark thing like we said, if, no to number 1, then we had a big dark arrow go to number 3, we had no more missing data. So we had no more. So it wasn't anything weird about the item that was offensive, hard to answer. It was because the instructions. So, you've got to address missing data. The book, I believe, discusses missing data very briefly, but I want to spend a little time on it, just a little time about missing data. It doesn't just, it just discusses it a little, but not a lot. So I'm not going to go through my whole presentation, but it's going to happen, everybody, and you've got to deal with it. The days of ignoring missing data are gone. You've heard me in 6021 talk about it. You've heard me in 6022 talk about it. The days of you being able to get a document by me, maybe other people, but by me, say you got 15 people, and because they didn't answer, our analyzable sample size will be 100 instead of 150. You may be able to pass muster with others, and ain't going to pass muster with me. You're going to have to address the mechanism of missing data. Is it random versus non-random? And start understanding the techniques that are very, very available for dealing with missing data. So, though it's more easily controlled for in controlled trials, it still can happen in experiments, especially with observational research, surveys, etc. Hence, you need to think about how you plan to deal with missing data before you collect data. It's like with power analysis. You think about it before you start your study. Okay, everybody, what do you think contributes to missing data? I've discussed a few. My instructions. Error. Absolutely.
Attrition.
No, but that's absolutely, that could be attrition. People drop out. Absolutely, with repeated measures, attrition. Even what do you do with don't know, not applicable responses in a survey? You ever seen DK or NA? Not applicable? If you have you're waving, you're saying yes, you've seen that, right? You can't give it a 6 and pretend it's part of the 1 to 5 point scale. I mean, you will give it a 6. You may give it a 6 because it's at the end of the item, but you're not going to average it in. So what do you do with that? If a lot of people, everybody, are using DK and NA, there's a couple of questions I have for you. DK means it's a knowledge-based question. Sometimes knowledge-based questions are masqueraded as opinion questions, or vice versa. I feel the war in Afghanistan has gotten too expensive. Strongly agree to strongly disagree. Yeah, you could maybe agree, but could that be a knowledge-based question? What knowledge might be appropriate for you to be able to answer that question?
How much does it actually cost?
Exactly, Chad, right? You may want to, is there a chance none of you in this room know exactly how much we have spent on Afghanistan and Iraq? Dude, and it's in the billions, right? You know it's in the billions, but do you know if it's 20 billion? Is it 100 billion? 850 billion? Does anybody know? So, you could say agree to disagree. You may say, oh, absolutely, I agree. It's too expensive. But do you see some people may say, I don't know. So if a lot of people are using this as an option in a survey, my question to you is, did you have a question that's a knowledge-based question? And did the right audience answer it? Did you have that item for the right audience? Otherwise, you may have to code that as missing data. A lot of people use the not applicable. Do you have the right audience? I am happy with the series of promotions that are available to me at my company. What if you're in a position that never gets promoted? Right? Or you're the CEO. I mean, there may, so you got, so NA, if you get a lot of people that have NA, if you have 8% are not, don't knows, and 12% are not applicables, 1%, I'm not gonna, it's not gonna strike an alarm for me as much. If you get something like this, I'm gonna ask the client, are you sure you have the right audience? Because you may have to code that as missing data, you may. So, lots of text on missing data. The classic is Little and Rubin's, statistical analysis of missing data. Parts of it, very readable, parts of it get a little complex. But then the last few years, there's been more missing data books. There's a little green book on missing data by Paul Allison. Then a gentle introduction. This one's almost too gentle, but very user-friendly. I love this one by Craig Enders. This one is kind of the mean of these two. Right, it's the mean of these. It gets into some of the technicalities, but also is very gentle. He's a social scientist. Great book by Craig Enders on missing data. And then even look at this one, statistical power analysis with missing data, both of them. But this book, I highly recommend by Enders. See, the thing is, and there's a few articles. I mean, this is just a few articles. There is one that I keep showing all of you every semester, Schaefer and Graham's Missing Data, Our View of State of the Art. This is a classic article you can download, and Graham's more recent one on missing data analysis, plus either Graham or Schaefer. I think Graham has a new book coming out on missing data. So the days of just ignoring it are gone, everybody, are gone. Just briefly, I'm going through this kind of fast because we've had this before, but I want you to understand the mechanisms of missing data. Missing completely at random, missing at random, missing not at random. And it can be ignorable versus non-ignorable. CON means you got complete data. Chad has answered every question. Observe, complete data, and OBS means observe. Oops, guess what? There's some missing data. What does MCAR mean? Missing completely at random means, you know what? You've got 150 people from a population. 20 are missing. And guess what? That 20 is just a random subset of the 150. It's a random subset. Which means the probability of R, where R is a missing data indicator. 0 means not missing, 1 equals missing. The probability of R, given the outcome, is just the probability of R, which means it's a subset. It's a subset. What does that mean? It doesn't depend on the observed data or the completed data. It means that the missing doesn't depend on the missing variable or all the other variables in your database. So if I'm missing on depression, you're not missing it based on your depression or every other variable, gender, race, etc. that's in your database. This is the most restrictive assumption. If I say most restrictive, does that mean you think it's the more realistic or less realistic? You got it, Zach. Less realistic. So that's missing completely at random. What's probably more likely is this. And the new missing data techniques are equipped to handle missing at random. This means, you know what, we've got missing data. You didn't answer 15% of the items on my job satisfaction inventory. But guess what? It's due to X but not Y. It ain't due to job satisfaction you're missing, but it is due to maybe, guess what? Oops, more males than females didn't answer. And you've measured sex. Guess what? Those with more tenure on the job tended not to answer versus those with less tenure. So it means that, you know what? The probability an observation is missing can depend on another observed variable. And basically, once you control for those other variables, there shouldn't be between group differences. Once you control for them, there should be between groups. This is the more realistic assumption. And you are almost out of luck when this happens. Not completely, but guess why? I'm sorry, what's your name one more time again, please? Layla? L-E-I-L-A? Layla. Layla doesn't answer her depression inventory because she's depressed. Why? Guess what? Missing data depends on why. You're out of luck. That's called not missing at random, and it's non-ignorable. In other words, guess what? Layla's not answering depression because I feel hopeless today, I feel helpless today, no one really likes me, my life is down in the dumps, shit, forget it, I'm going to go drink. You know, so that being said, it depends on why, and you don't have any information, right? Because it's missing, and that there are missing data. Well, I should have had this on. Hang on for a second. Could be IT. Dale Glaser. Oh, let me talk to you. I didn't know I had it on. It's my class. I thought it was the IT person. Let me talk to you later. Bye. Sorry, it's my wife, you guys. I never have this on. I was hoping it was the IT. I now text. I bought one in August. I text now.
I say that's it, but you don't have your wife programmed in your phone, so you know it's her.
No, should I? No, I haven't done that. No.
I can show you later. We can even give her her own ringtone.
Okay. But so anyway, so there's missing data on depression. So this is what computers do, you guys. This is what all the multivariate techniques will do. List-wise deletion. This is what the repeated measures, your MANOVAs, all the fancy schmancy stuff you're going to learn in this class. Discriminant analysis, canonical correlation, multivariate regression. All those are going to have as the default list-wise. Complete case analysis. We want all the data for all the people. Right? Unfortunately, guess what? A, practically speaking, do you lose participants? And you get biased parameter estimates. What does a bias mean? It means that for some people, that regression coefficient will overestimate. For some, it'll underestimate. Absolutely. Right? The notion of an unbiased is even if once I do repeated sampling, the mean of these will equal the population parameter. And there's always going to be a little bit of under and overestimation. But the only time list-wise kind of works is when you have an MCAR assumption, missing completely at random, which is, again, pretty restrictive. So you guys, there's enough evidence out there to show list-wise deletion is problematic, and it's the default. It is the default. When you go and do even something as simple, right? Even do something as simple as analyze, regression, linear, and go into options. Look what the default is, list-wise. Now, the next option. So if I have 146 people, oops, guess what? I do multiple regression, which will be your second homework. Guess what? So 142 exercise, 143 diet, 123 people. You went from 123. 23 people is not a trivial loss of data, everybody. It is not. I know you say, well, Dale, I still have 123 people, which is pretty good. You lost a good chunk of people, and you're going to have to convince me that 23 people are what? Random or non-random for you to proceed? Well, I'm going to want you to furnish evidence for those 23 people. Yeah. You're going to have to come up with some pretty compelling evidence, which ain't easy, to say that they're a random subset before I trust your regression coefficients, before I trust any of these.
How would you do that?
Well, that's the thing. I'm going to show you one test in SPSS, but you know what? It's hard to show evidence of this. Even MCAR, some people say, I'm going to go ahead and show between group differences on all my other variables. I'll create a missing versus not missing data indicator and do t-tests and chi-squares on all these other variables I have. And if I don't have significance on any of them, I have evidence it's MCAR. Well, there was a recent article that says, how do we know you haven't looked at other important variables? So, you know, proving any of them is really hard, Zach. It's just absolutely proving them. Pairwise deletion. This person has all the data. Do you see person number 1 has all the data? Person number 2, oops. Person number 3, guess how many people will be analyzed for pairwise? All of them. Because he uses the available information. There's a problem, though. What's your sample size? It can vary. What if 25 people have X1 and X2, 28 people have Y and X1, and 30 have all 3? You got all these sample sizes, right? You have all these different sample sizes for pairwise, which means standard errors are problematic. You can get what's called a non-positive definite matrix. You're going to learn to love matrix algebra in this class. And what a non-positive definite matrix is have you guys lately tried to do something like this, 3 divided by 0. Okay, you probably will get a little thing called E, which means an error. Can't divide by 0. A non-positive definite matrix means all of a sudden I get some weird estimates here in the denominator that I can't invert my matrix. You're going to learn what inversion means. It's a fancy way of putting a -1 there, which means dividing a whole matrix of numbers. And you're going to learn what this means later. And the fact is, you get weird stuff like that with pairwise deletion. And there's no set sample size. So I would stay away from pairwise. It's an option in SPSS. Look at good old regression. Homework number 2. You can get a little thing called pairwise. That's a problem. Pairwise deletion. Wow, 143 there, 142 there, 138 there, 140 there. Sample sizes are kind of all over the map. Now, what I'm not going to get into here is other options. I don't want to get too deep into this. This is for you. If I don't lecture on it, it won't be on the test. What's open game is for stuff I've lectured on, like maybe the mechanisms of missing data. But there are other options that I won't lecture about right now. Things like regression imputation. Regression imputation quickly is, I go ahead, for 20 people that have data on X and you're missing on Y, I can run my regression solution, get my equation, and I'm just going to go ahead and for my missing data, I'm just going to fill in and put in that predicted score. I get a predicted score for that person, because if you have information on X, you'll get a predicted score. You'll get it, and I could plug it in, everybody, and now save all 146. But there's a problem with regression imputation. Because if I use a predicted score for Y, and put that as my new Y, guess what? That subset of cases will be perfectly predicted on the regression line. See, you don't see that here as much. Do you know why? Because think about it. The correlation of Y and predicted Y is going to be 1.0. Right? Predicted score and my new Y. It's going to be perfectly predicted. Which means, guess what? You got bias. What comes closer to the more modern techniques is this thing called stochastic regression imputation. And basically what that means is we know that an R square of 1.0 is not realistic. Because guess what we usually have when we predict someone? When we predict someone's violence, organizational commitment. You're usually, when you predict a score, you're usually going to have
0.3
error. Error, or what we called in regression, Y minus predicted Y is a residual. Now there are techniques where I can add the residual. I can create a normally distributed matrix, which I did there, of residuals and add it to each one. Which means I'm adding that element of uncertainty. And now we don't have that subset. So these are all options, everybody. Do not use mean substitution, which is an option in SPSS. In other words, I just plug in the mean for the variable. If the mean is 3.0 for item 1, someone's missing, I'm just going to plug in a 1.
That's just making something up.
Well, no, it's a mean from a variable, right?
But if there's not a data point there, you can't just...
Sure, I can. Look, 2, 1, 0, oops. The mean is 1, right? This is missing. I'll just plug in a 1, because it's the mean. 2 and 1, 2, 3, yeah, divide by 3 is 1. Or no, you know what, I'll just use those two. 2 and 1, I'll just plug in a 1.5. There we go. You see why I plugged in a 1.5?
Yeah, I see why, but...
Yeah. That's called mean substitution, which was used a lot. It's an option in regression. It's called mean substitution. However, guess what you're putting in? Let's say there's 30 people that are missing, and you plug in a 1.5, 1.5, 1.5. Do you think you're decreasing or increasing variability by putting in a constant? And when you decrease variability, do you think that'll render a bigger or smaller correlation? Smaller. Right? Because correlations love variability. You put in a constant. So if you think about it, everybody, all of a sudden you're going to put in a constant. I mean, you're going to have all these cluster of cases as a constant. So it decreases variability. So stay away from mean substitution. Albeit, I do want to point to one article by Roth and Switzer, Organizational Research Methods. They actually found some promising techniques for missing data, missing mean substitution for the person, for multi-item scales. And it's not bad. I've used it a couple times. It's called person mean imputation, which I know sounds a little painful, but Zach is 30. He'll be okay with it. So here we see that for this person, they have a 4 and a 2 for 2 items. The mean for that person is 3. Let's just plug in a 3. So it's a 4-item scale. 4-item scale on adaptability to organizations. And I plug in a mean for the person, not for the variable. This article showed it ain't bad. What I've done in this handout is giving you the syntax, how to do it. You can cut and paste from this, everybody. Here's the exact syntax, how you can go ahead and create the scale mean for each person, which takes into account the number of items they've included. See, if you just did give me the mean of this, it'll think everybody's answered, up to 4 items. Well, some may have only answered 2 or 3. This syntax takes into account that some may answer 1 item, some may 2, some all the way up to 4. So that is one possible option for multi-item scales. But there's much more modern methods. And these are ones I'd like you to at least know about. Basically, maximum likelihood methods and multiple imputation. And soon you're going to see maximum likelihood is the mathematical brains behind logistic regression, categorical data analysis, structure equation modeling, and multi-level modeling. So, maximum likelihood. And let me see if I say anything about these in the notes. So, list-wise, not so hot. Partial, less hot. Okay? We've discussed the mechanisms of missingness, and they're in your notes, and now also in the PowerPoint. And again, here's the Psych Methods article by Schaefer. Both of these are available. Maximum likelihood, both of which are available in SPSS Missing Values module. There's a Missing Values module and MI module. Or maybe part of both in SPSS, I'm not sure. So, let me briefly show you in this PowerPoint. And I'm not going to get knee deep into this, but the goal of maximum likelihood is to find out the parameter estimates that maximize the likelihood of the observed data. I know that sounds weird. Parameter estimates, a variance, a covariance, a correlation, a mean, a standard deviation that maximizes the likelihood of what you got. So the best way I could present this is Embretson, who's presented a lot on this at APA, did a great way showing it. Let's say there's your mean. There's your observed data. Okay? I'm blindfolded. Warm or cold?
Cold. Cold.
See, so I get parameter estimates that get closer and closer. So you've got a normal distribution. Let's say the population mean is 15. Let's say the population mean is 15 on a job satisfaction scale. And that's the mean, or the observed data. Pretty low probability of these, huh? Will it get a little bit higher? So maximum likelihood, it's almost through integration. It can integrate all these possible values and compute the likelihood of the sample data given these parameter estimates. Which means, don't ever want to do this by hand. It was computers that saved the day for this stuff. In the early 70s, when computers finally caught up with the mathematical notion. Because, you know what you got to do with this stuff is this. There's no way you ever have to worry about these formulas. But here what you find is the way to look at this is briefly. And you don't have to worry about this. You have to have the joint density function for all observations. What does a density function mean? Do you guys remember good old z-scores? If someone's 1 standard deviation above the mean, they're at the 84th percentile. That's the cumulative distribution. The PDF is right here, the probability density function. And it's called H, or the ordinate, the height of the curve. So if someone's got a 35 on an exam, I not only can see their 84%, I can also figure out the height of the curve. What maximum likelihood does is it takes all these possible densities, all these densities, which is a lot, and then multiplies them. Multiplies them. How do I have to do that by hand? And it computes the likelihood. And then that means this uppercase pi means you take the product of all these likelihoods. And that's it, everybody, which means you need computers. You really want computers to do that black box stuff. And that's the brains behind a lot of these statistical techniques for this semester. Because what you're going to soon find, as soon as you get some things that look like this, and they get stuck here. In calculus, we call this a local maximum, and this is called a global maximum. Sometimes we get stuck here with maximum likelihood, and we want to go over there. Sometimes you need to give it a little shove to optimize the solution. And that's when you start getting problems with some of these algorithms. So that's maximum likelihood, everybody. That's kind of the black box behind the computer. And with continuous variables, look, a mean minus a mean, and you can even put in correlations, covariances, all this information, all these parameter estimates that maximize the likelihood of the observed data. So what's really cool about missing data and maximum likelihood, it'll use all the information. It'll integrate across each person. So if you answered all the items, if you missed 2, if you missed 3 items, Jocelyn misses 4, Stacy misses 3, Zach answers all, it'll go ahead and use all the available information. All the available information. Create a matrix for each one of you. A variance, covariance matrix, and a mean vector for all these variables, for multiple variables, and basically using all the complete data points. And soon we're going to talk about Monboy distance, which you were actually exposed to in regression when we looked at leverage, and because leverage times n minus 1 was Monboy distance, and it's a type of z-score. It takes the mean minus the population mean and transposes it. Guess what? This is going to be matrix algebra. Because now you don't only have individuals, you also have multiple variables. So it can take multiple variables from multiple people with different levels of missing data and be able to get a solution. Pretty cool, huh? A lot better than list-wise deletion. That's maximum likelihood. That's maximum likelihood. Probably need a computer for this, huh? How'd you like to do that by hand? No. Because you have to do it for each person. No, don't worry, Jocelyn. I won't have you do it. I'm not going to get into the EM algorithm, but this is what SPSS uses as one option. SPSS has a missing value option, and you have 2 steps. The first is a regression imputation. I'm just going to go and predict, given all these possible combinations, y and x1 and x2, which is probably list-wise deletion, and I'll impute the regression score. Then I will maximize that. But there's still those problems. It still uses regression imputation, which means you're going to perfectly predict that y variable. SPSS, though, does have a missing value analysis. It's got the EM algorithm, and you can save a database. And literally, everybody, the database will have, here's list-wise, pairwise, we'll have all 146 people in there. You can save it, the database, and it'll impute the values. It'll impute the values for 146, but there's a problem. You're using regression imputation for those 23 cases. So, American statistician did a review of all these missing value modules, and it really criticized this in SPSS. It ripped SPSS a new one because it creates this new database, 146, but it still used regression imputation, which, again, the regular user probably wouldn't know that. But now it literally imputes a new score in your database that you can save. Now, you asked me earlier, are there statistical tests for this? There is one in SPSS called Little's MCAR test. In other words, it takes into account all these variables, and it essentially standardizes the difference between subgroup means and grand means on each of the variables. So if I have 6 variables there, it'll take all the combinations of variables, and you hope it's not significant. But there's a problem. It takes all the variables in one formula. You don't know which variable is the contributor. You don't know which variable mainly is most problematic. So some people say, I've had a couple dissertation students that say, if it's not significant, they don't worry. The data is MCAR. And then I always write back, you might be right, Or there may be auxiliary variables that you didn't include. Guess what? You didn't include ethnicity. You didn't include job satisfaction. So, but basically, everybody, maximum likelihood, which may or may not use the EM algorithm, is one of those cutting-edge techniques. What I do, if I was going to use the EM aspect, the EM option in SPSS, I would not use the database. I would use the variance-covariance matrix that you can save. And I would use this, which is proper, from the EM algorithm and impute it into any type of structured equation modeling program. Or even in regression, and use it. And I want to show you one program, even though you'll use Amos, I use an SEM program called M+. I think it's just one of the best softwares out there. And I can go ahead and save the means, standard deviations, correlation matrix. I can do that, or the EM matrix. And what's kind of cool, everybody, I can run the regression and get the correct solution. So I just want you to be aware of, with maximum likelihood, that that is one option you should be aware of. And here's some practice. That's MI, that's maximum likelihood. The other one that's become very popular, everybody, very popular, and I just show this using this in other programs. M+ is really easy to do maximum likelihood, very easy. All you have to do, everybody, for maximum likelihood is give a code like 999 for the missing data. Like say just have an integer. And missing equals all. Remember we had 123 people, everybody, with full data. And look what SPS M+ does. There's 12 missing data patterns, and it ended up using 146. And I could do my regression. Multiple imputation, and Amos. Amos, if you decide to use Amos, which is licensed here at Alliant, this was one of the first structured equation modeling programs that was equipped to handle missing data. Amos was one of the first ones which used maximum likelihood. What you're going to like, and you're going to get so much better at this than me, I'm really bad at drawing the pictures. You guys are going to get really good at it. I just don't have much patience to make it beautiful. I've seen people here with the PowerPoint, just, you guys are great at it. I'm graphically challenged. I know what I need to have in there to estimate it, but these are my 5 predictors, and this is my error term. And all you have to do in Amos is hit this box called estimate, means, and intercepts. That'll use maximum likelihood. So it's really easy to accommodate missing data and to use all the potential sample size. And then you get the proper regression estimates. Multiple imputation is the second major option for missing data. All multiple imputation does is it takes multiple databases and pools them together. So let's say I have a sample size of 146, and I take one database, 2 databases, and uses an imputation option, which comes really close to the stochastic imputation, which means I add the element of uncertainty. I add an error to every single person from the missing data, and I do it across maybe 5 or 10 or 20 databases. And so, I'm not going to get into Bayesian estimation, but I feel that there's even a book coming out for Bayesians, for basically social scientists. I think Bayesian modeling is going to be really big in the social sciences. It's been big in medicine for years. Basically what Bayesian is, you specify a prior distribution. Meaning, guess what? You put information in. You put information in. See, this is what we do with significance testing. The probability of y given your hypothesis, right? Probability of the outcome given your hypothesis. What about this, everybody? Probability of hypotheses given y. It's the opposite, isn't it? That's called the posterior distribution. This is what the Bayesian predicts, called the posterior distribution. A posterior uses what's called the prior and the likelihood. The prior is prior information you have. The likelihood is y given x. This you have to put in. You think there's a 20%, you know from research that 20% of people recommit violent crimes. 20% do that. So you can put in prior information, which is interesting, meaning you have to go ahead, and which means it's as good as the information you put in. And that's multiple imputation generates several copies of data and imputes each copy with different estimates of missing values. So it goes through a cycle, and basically it fills in the data sets, combines the data set, and the software computes the proper standard errors across these data sets. Some people say you should have at least 50 data sets. Some say as low as 5. And SPSS does have an MI option. Maybe not necessarily the one you have access to at school, because it's a separate module, but there's a multiple imputation that you can use, and it'll create. I told it to create 5 data sets, which is exactly what it did. I create 5 data sets, and it pulls them together. Here's data set 1, 2, 3, 4, 5, and the pooled data set. I get an R squared for each one. And when all is said and done, everybody, I get a pooled regression coefficient for each of these data sets combined. So it literally creates, if you have 200 people, it'll create a data set of 1,000. Because 200 times 5 is 1,000. But you don't analyze it as if it's 1,000. You do what's called a split file, because SPSS knows it's a multiple imputed file, and it takes into account that element of uncertainty. So MI, and it's really easy to do MI and M+, which I show in the overhead. You don't have to worry about it. I think one thing that you might find of interesting, on the 60th slide, I compare all of these for this basic multiple regression. I compare list-wise, pairwise, SPSS regression, EM algorithm, FIML from M+, Amos, and you can kind of get an idea of how they're similar. Some are exactly the same, everybody. M+ and Amos, FIML, exactly the same. List-wise is by far the most different. List-wise is by far the most different, even looking at the different R squares. So I highly recommend that you guys at least get up to speed on multiple imputation and maximum likelihood. I think the days of just ignoring are gone. The days of ignoring missing data are gone. At this school, I'm not certain. If you get a committee members that don't know anything about it, you'll probably be fine. But hopefully your conscience will not let you do so.
What about multi-level modeling? As I was reading that, you handles missing data well, but is it not really accounting for?
Pretty much, yeah, it depends. Different software do different things.
Yeah.
Some of them will use what's called full information maximum likelihood or restricted maximum likelihood, and it will accommodate. And what's great about it, on the final lectures, we'll talk about repeated measures. If one person has 1 measure over time, one has 5, it'll use all available data. So it doesn't impute there, but it'll use all available data via maximum likelihood. How do we feel about mean substitution, everybody?
I don't like it.
Excellent. So you will not use mean substitution. Again, mean imputation for the person has some promise. Again, a lot of stuff that's in the notes is now in that big PowerPoint slide, which I just created. So you will want to refer to that for the test. There's one free multiple imputation program called NORM. I played with it back in the 90s when it was a DOS-based program. It's free. I have no idea. It was kind of kludgy, but it is free, so you may want to play around with it. I also want you to know, everybody, that for almost each of the chapters, I not only have notes, I do have handouts. I don't know if you've taken a look in Moodle, but you can minimally, I'd like you to print out the handouts before the lecture, because I will be going through sometimes the statistical results, and it might be easier for you to jot down notes. I don't expect you to print out the notes, and as you know, they're going to get longer and longer as the class proceeds. But at least print out the handouts which give you the statistical results that we'll go over in each class. So here I just show you again how to do this with M+, using multiple imputation, and I'm not going to go through that now. But I use these now for all my data, everybody. I use these for all my data. So you should be aware of the missing data techniques. That's why I created 2 presentations for the faculty here. One on power analysis, one for missing data. I did it for the benefit, not only of the faculty, but so that they can also be working well with you to make sure you're doing it right. And you understand these recent advances. So levels of measurement, a quick review. Nominal, you've been through this a million times, so you're sick of it. Sex is what? Nominal, right? Does the following make sense? Make sense. The average sex has a mean of 0.50, and the average person in this class is a hermaphrodite. Good. Are you ever going to do a histogram for a nominal variable? Thank you. You'll do a bar chart. Yeah, you'll do a bar chart. So that's nominal, right? It's categorical. Ordinal, first place, Padres, Giants, Arizona. I just thought I'd put Padres first place just for fun, because I know that's a fiction. but that being said, it's hard. They're not equidistant, are they? But you can rank them, right? Or it could be a self-report scale. Exercise is something I plan into my weekly schedule. Strongly disagree to strongly agree. Both of those are ordinal, even though there's a fascinating recent article, right? I want to... Interesting recent article in Psych Assessment. I think it's like January of 2013, something like that. That shows relationship of ordinal self-report item and continuous level construct. For example, maybe systolic blood pressure, right, which is very continuous, and self-report stress. And how on scatter plot they may have log relationship. What do I mean by log? Exponential. That's a fascinating article that shows I have my 1-point scale, 2, 3, 4, 5, and then blood pressure. And that, if it's kind of linear, you may make an argument that the ordinal is kind of interval. Maybe. If it's like this, maybe there's something going on 4 and 5 on stress as opposed to 2 or 3. It's a really interesting article that I'm going to try to keep in mind to make the compelling argument that this is ordinal or interval. Now, what does interval mean, everybody? The distance between each of these is what? The same or different across the entire scale. Yeah, is that a harder argument to make, Zach, for self-report? Is it hard to say agree to strongly agree is exactly the same there? I mean, maybe it is, maybe it isn't, right? Maybe when I go from disagree to strongly disagree on a political item, like abortion is the same as murder, maybe that's a much different change than neutral to agree. Right? That could be a very, very different type of even phenomenological change. So interval assumes, like temperature, 99 to 100 is the same as 102 to 103. But what about an earthquake? Is a 3.6 to 3.7 the same as 6.9 to 7.0? Huge. When it goes 6.9 to 7.0, is that a big difference in damage? 3.8 to 3.9? Supposing they happen all the time here, right? San Diego, Mountain Lion Desert. And what's the highest level, everybody? Ratio. How many hours do you exercise per week? Can anyone exercise 0 hours? Is that possible? Would you say 6 hours is twice as much as 3?
Yeah.
So that's a ratio. So for a lot of these multivariate techniques, just like regression, we're going to assume they're interval level, but you're going to find, what if you have a dichotomous outcome? You're going to learn about discriminant function analysis and logistic. What if it's ordinal? In 602.2, I briefly exposed you to proportional odds modeling or ordinal regression. We'll talk a little bit about that. Structured equation modeling techniques can handle nominal, ordinal, and they have different types of estimators they use for those. So, this gets, remember we've discussed this one? I started playing around with this last week, and this is a pain scale. What if I was asking you about your marriage? I decided to put a new descriptor on it. So your marriage, no distress to invariable. If you give a 2 and you give a 4, are you willing to say your marriage is twice as, from uncomfortable to annoying on the marriage level? But yet, when we have a 0 to 10-point scale, you will use your MANOVAs, you will use your regressions, because first of all, a lot of times they may be normally distributed, and using ordinal techniques for 11-point scale might get a little cumbersome. So these type of scales gets tricky. What do I do personally? If it's radically skewed, everybody, if a lot of people said they had no distress, there are statistical techniques, such as non-parametric statistics, or even these other types of regression models they'll handle when you have lots of zeros and ones. Transformations ain't going to help with an ordinal scale. I guarantee you, you're not going to be able to transform this. Otherwise, you could use your ANOVAs and use the famous, it's robust to these violations. Maybe, maybe not. Now, Linda Mutain from M+, and you know, even with 5-point scales, you do pretty well with the ANOVAs of the world, the MANOVAs, unless you have this. If you have you guys remember what a ceiling or floor effect is? If you have a strong, a lot of people said great or horrible, then things can get really screwy doing your MANOVAs. So, but usually, do we usually analyze individual scale items or composite of items? What do you guys think generally? Do you generally analyze individual Likert items or a composite into a scale? What do we tend to do, everybody, at least in the social sciences? A scale. Right? We combine 5 of these items, and then you start getting kind of a continuity. So that's your basic levels of measurement that we will address this semester. Normality, right? You guys all know about the normal distribution. In both classes we've discussed transformations. Here's a cost variable. Cost adjusted for inflation from a database, right? 1,341 people. Tell me in your opinion. Perfectly normal? How do you describe it? Positively skewed, skewed to the right or skewed to the left? Yeah, I know it's skewed to the right. I know you can't see it, but there's an outlier right there. Right? And I know it's hard to see the outliers here because there's not that many. How's it look? Yeah, that's the log transformation. Right? All I did was take a log. Still kind of have a little bit of an outlier there. But do you see the log transformation helped? So this is when people start thinking statisticians are playing with numbers. If you took the log of 100 in your computer, on your calculator, using base 10, log of 100 is what, everybody? Using the base 10. So if you make $100 a week, you're not making $2 a week. You're making the log of 100. So the descriptive stats make no sense, but it sure might help with the assumptions in regression. Even though in regression, we're going to discuss what? The distribution of the residuals or the outcome. What have we said 1,000,000 times at 6022? The residuals. But didn't that do a great job for the ANOVAs of the world? And wow, everybody, look at the effect sizes. Look at my ANOVA, everybody. 6.7% for the untransformed, 12% for the log. In your opinion, does that seem like a big difference? Does going from 6.7 to 12% seem like a lot? Huge difference. Now, I'm not saying you will always gain power when you transform. In fact, sometimes I've seen it decrease. But that's a huge change. That's a huge change, everybody, using the log transform. But remember, it's going to be weird to report the descriptive stats, isn't it? It's not going to make sense. But you can report the F, the effect size. Now, there are some people that do not like transformations because you're getting far away from your actual metric. Right? You're getting far away. Let's say the average age in your workforce is 49, and the square root transform does a beautiful job of normalizing. So is the average person at Qualcomm now 7 years old? Square root of 49 is 7. So it's not going to make sense. But it could just help meet some of the assumptions. Outliers. Okay, I have 8 more minutes. Outliers, we're going to discuss this again in the regression chapter, which will be a nice review for you that had 6022 last year. And for those who, you're going to be having outliers not till chapter 10, so it'll be a precursor of things to come. Outliers can have a huge impact, especially on what, small or large sample size. Yeah. But you know, you guys, Hewlett-Packard study, I always refer to this because I was so surprised. 324 companies working with the printer division, 4 outliers. I thought 4 outliers for 324, big deal. I was surprised that our score changed from 20 to 24%. If you had asked me before, just a multiple choice, do you think there's any way you can add 4% from 20 by just 4 outliers? I probably would have said, probably not. For 100 people, I would have said, yeah, maybe. 300, it wasn't. So even, I want to say, even outliers can have an impact even on larger data sets. So, you recall 6022, Malavoy distance, leverage, descriptivity. All of these were discussed in detail in 6022. What you're going to find is I'm going to be exposing you to a really cool macro that'll analyze not only univariate normality and outliers, but multivariate. It's not an SPSS, but it's a macro that you guys will start using for this class. But let's say we have a histogram here of health maintenance, how well you maintain your health. Is that perfectly normal? A little bit of an outlier down here, huh? There are some outliers. And as you know, you can use the Explore. Remember using the good old Explore option in SPSS? Outliers, percentiles, getting a feel for your data. Remember the good old test of normality, everybody? Remember the good old test of normality? Were we happy or sad when we had significance?
Sad.
Sad, right. But what did I say many times? Don't just rely on p-values. Look at the picture. Because is it possible with large sample sizes, it may be somewhat normal, but guess what? You had a large sample size. And large sample sizes tend to give what? More or less power. Larger the sample size, the which is easier to reject the null. So again, everybody, look at the histogram. Look at the histogram, and you could do a log transform, and you could do a lot of this by point and click. You can actually put in the name of your new variable, put log 10, put in health maintenance, and see if it helps. So again, look at skewness, and do you remember kurtosis, everybody? Remember we had lepto, leap, and what was our favorite marsupial? Platykurtosis, which is flat, right? So remember all of these kurtosis ways to look at your variables that we discussed many times. However, there's no real test for multivariate normality, multivariate skewness in SPSS, except Larry DiCarlo wrote this wonderful paper in '97 on the meaning and use of kurtosis in psych methods. And you can test univariate skewness. You can do an SPSS by hand. You could take the skew divided by the standard error, and it's a type of z-score. You can take skew, divide kurtosis by standard error. It's a type of z-score. Right? And the good old value for z in alpha 0.05 is plus or minus 1.96. So if you took skew divided by standard error, kurtosis is the square root of kurtosis divided by standard error, and the null value is 0. So you can actually test these by hand in SPSS for univariate. Now what about multivariate tests? They are not available in SPSS, but we have a wonderful macro that I have appended on Moodle that I want you to get your feet wet with, everybody, on one of the further future homeworks. For multivariate outliers, you can use for homework assignment the DiCarlo macro that I have appended under in-class data examples titled Norm Test DiCarlo. Or you can download it from his website. You've heard me talk about this in a couple of my other classes, but it's a wonderful macro, and I have appended it. Bless you. Oh, there it is, Here's the macro that you never have to worry about. Lines and lines of code. You don't have to worry about everybody. Even though sometimes you have to finagle it, and I just learned how to do this thing called all subsets regression. I did have to do some stuff in the macro. All you have to do, everybody, is 2 itsy-bitsy lines of code. All you have to do is 2 itsy-bitsy lines of code, which means it's called an include statement. The include is a global statement to invoke a macro. So what is a macro? It's lines and lines of code that people have created, made freely available to do stuff that SPSS inside won't. So first you have to define where you save your syntax file. You know, save it on chad/align/normtest. Just you save it somewhere. And then normtest, you just put in all your variables there, the names of the variables. Usually these include statements have like 1 or 2 lines of code. And that's the macro, everybody. That's the macro. And what's really, really cool about it, it gives me the actual z values you don't have to do by hand. You can do it by hand if you like, but here's the univariate for each of my variables in the database, which is here, everybody, the database. Just so you know, if you want to practice with this and replicate, if you do File, Open, Data, everything's working well now. It takes about an hour.
That's how it is for me.
Databases, health survey, in-class examples. So, I've got, these health, I've got all this stuff for you. Everything's available there for you to replicate for funsies. And you can see significant for exercise, significant there, not significant there. So they're all significantly skewed except for social influence, because we don't want significance. But look what else it gives me, everybody. It gives me the test for kurtosis. Pretty cool. It gives me all the z-tests for kurtosis. All of these are good for kurtosis. And it gives me also this thing called omnibus test of normality. It's an omnibus, which kind of takes into account a little bit of both skew and kurtosis. And overall, the two variables that are okay is diet and social influence. So again, it's just another test for omnibus test. But here is what's really going to be cool for this class. It gives you a multivariate test. So there's a couple options here, everybody. You got multivariate skew, you got Small's test. I would just use Small's for now. Do you see, everybody? It's significant, which means the combination of all these variables together are multivariate skew. It's kind of what you'd expect. And look what else you get, everybody. Multivariate kurtosis. All of these together, looking at Small's test or Mardia. Mardia has pretty good properties. But this is slightly different. It is significant. So I would use the Small test, and we see it's not significant. If you're more conservative, you use Mardia's. And here's your omnibus test of multivariate normality. This is going to be a really nice one for you to use, everybody. This is based on Small's test, and it's the omnibus test. Here's the biggie. Happy or sad, everybody, with a p of 0.008. Happy or sad?
Oh, we're looking for normality, no, then we're sad.
Yeah, there it is, guys. So what's really cool is by learning DiCarlo's macro, you just save. I've got it already for you on Moodle. You save it in your subdirectory of choice. So you just type in the include statement. You can cut and paste from my syntax. And then just type in the variables using the same syntax. And you can get a test of multivariate normality. If you want to, it is on his website. You can download it from there too. Or you might as well just save yourself time and just download the syntax I put in Moodle. And it also gives you, by Mohawk distance, it gives you which cases are maybe most problematic. It'll actually show you which case has the highest Monboy distance, which means if I have these variables in space, what we call centroids. Kind of sounds like Star Trek. Darn it, bones, get rid of those. So it sounds like Star Trek. We got these things called centroids, and you may have a point over here. But this is a mean of one variable, mean of one, and person number one may be way over here. So it kind of gives you an idea that if you wanted to, you could start making sense of potential outliers. So you'll practice this with homework number 2 when we get to regression. And I do want you to get your feet wet with this.
Why do you prefer this method for assessing normality from multivariate? Or is this the only one?
Yeah, you're right. They don't have one in SPSS. Built in, they have the univariate one. This has the multivariate. It's got the more, I think, the most up-to-date algorithms. So here's a checklist from Tabachnik and Fidel. Inspect descriptive stats for out-of-range values. Look at means and standard deviations. Missing data. Is it a problem? Need to address it. Address the distribution, skew, kurtosis, and if warranted, transform. Identify with outliers. And now you know about DiCarlo's macro. So this, everybody, will actually apply to almost every technique with respect to assumptions. And in chapter 3, we're going to